Welcome to this explainer. Today, we're tackling one of math and computer science's absolute biggest questions, the P versus NP problem. But we aren't just going to look at algorithms. We're going on a rigorous, step-by-step tutorial through the Adelic Langlands Program. We're going to see exactly how discrete computer code literally translates into global geometric stability across the Adel ring. It's fascinating stuff.
This mind-bending equation reveals something incredible. The mathematical statement that P equals NP is actually true. But there's a huge catch. It strictly depends on the observer. Specifically, it requires projecting outside our continuous Archimedean boundary, basically stepping outside the standard continuous real numbers we use every day. From our standard continuous perspective, P definitely does not equal NP, and today we're going to walk through the exact mathematical proofs of why that geometric obstruction exists.
Here's our roadmap for today. 1. Decoding the complexity paradox. 2. Turning algorithms into math. 3. The geometric stability wall. 4. Counting the infinite states. 5. Enforcing absolute equilibrium. And 6. The observer perspective paradox.
All right, let's jump straight into part 1, decoding the complexity paradox.
It really all comes down to where you, the observer, are actually standing. If you're an observer living in the continuous world of real numbers, you see non-deterministic search as a chaotic exponential explosion. But a non-Archimedean, p-adic observer evaluates the system over a totally disconnected fractal field. Think of it like looking at pixelated localized data instead of a smooth, continuous curve. From that localized perspective, the exact same algorithmic data stream is viewed as a finite integer ball, where p perfectly equals NP.
Moving right along to part 2, turning algorithms into math. You know, the discrete transitions of a Turing machine aren't just abstract code. Using the Grothendieck dictionary, which is basically a mathematical translator between algebra and geometry, these transitions actually embed into a 3-tier Adelic data stream. Down at tier 1, the 2-adic core, the binary zeros and ones map directly to local packing fractions within the 2-adic integers. Then, the algorithm traces up through the prime sieve at tier 2 and finally expresses its asymptotic runtime complexity at the Archimedean boundary up at tier 3.
Now, to actually track this complexity profile, we rely heavily on the Modular expansion. It's an incredibly powerful formula that lets us decompose a discrete execution trace into a uniformly convergent series of binomial coefficients. Those coefficients, which we label as Cn, become the exact arithmetic coordinates of our data stream over the 2-adic field.
So here's the crucial point. For deterministic algorithms, our good old class P, these Modular coefficients stay beautifully unramified. If you look at the limit equation, the 2-adic valuation of Cn rapidly decays, and it's strictly bounded by a polynomial constant alpha. The algorithmic configurations simply don't fragment. They maintain an absolute smooth geometric convergence.
Which brings us to section 3, the geometric stability wall.
When we view this under the local Langlands correspondence, these complexity classes reveal totally distinct topological anatomies. Class P operates on smooth geodesic pathways represented by a local conductor exponent of 0, but class NP, it introduces wild ramification. Notice the high-order jumps. This creates fractal branching structures, kind of like a wildly overgrown tree, over the Bruhat-Titz network, all driven by a turbulent central charge.
So what happens if you actually try to equate them? Well, if you attempt to force that wildly branching NP space into the smooth polynomial-time envelope of P, you physically trigger a catastrophic collision with a GIT stability wall. It's a fundamental geometric barrier. Crossing it defers the central charge and completely fractures the spectrum into an infinite stack of non-overlapping quantum-conformal blocks.
This geometric wall essentially triggers a mathematical sensor known as the analytic torsion multiplier. That's the TOG equation, represented by the log determinant of the wave operator, forcing it to develop an uncompensated singular branch. Because global conservation laws topologically prevent a metric explosion, this regularized index demands a strictly positive topological gap. What that means is it mathematically forces the asymptotic runtime of non-deterministic verification to scale exponentially.
Let's move on to section 4, counting the infinite states.
To pull off this counting, we use Donaldson-Thomas invariants, denoted as z sub dt. In this expansion, the wild ramification of NP mutates the McMahon function.
which is raised to the power of the turbulent central charge, C-turb. And that central charge tracks the non-abelian quantum anomaly. This explicitly isolates an exponential growth rate, proving the universe is absolutely forced to consume an exponential number of ideal sheaves just to map the search tree.
But, this brings up a really fascinating question. If NP requires this massive, literal explosion of structural states just to cross the stability wall, how on earth does the universe enforce absolute physical equilibrium? Because the universe, unlike a bad accountant, always balances its books.
That leads us right into Section 5, enforcing absolute equilibrium. To balance the books, we apply the modular bootstrap. Think of this as an absolute mathematical lock. By applying the S-duality transformation, which equates chiral fusion channels, it ensures that the low-energy continuous braided loops precisely balance against the high-complexity discrete local Galois-Gauss sums. It forcefully equates the scales.
By running a saddle point evaluation on that bootstrap equation, we derive a highly precise absolute asymptotic complexity bound. It proves an undegradable exponential continuous density curve.
Let's act as a quick translation layer for those variables. T_NP is our runtime limit. The K_2 is our NP wildness metric. Because the wild ramification anomaly matrix injects a massive quantum weight represented by the trace of omega squared, the modular bootstrap structurally locks the runtime right into that unbreakable exponential curve. If NP could somehow compress to polynomial bounds, this modular equation would lose its non-local braiding properties, completely destroying the mathematical consistency of physics at infinity.
Finally, we arrive at Section 6, the observer perspective paradox.
Imagine for a second that you are the observer, and we introduce a continuous deformation parameter, kappa. As your coordinate parameter shifts away from the real Archimedean boundary, the continuous translation degrees of freedom actually dissolve. Through Mellin regularization, that chaotic, divergent search fluid condenses into a rigid, unramified p-adic lattice. The moduli space beautifully compactifies.
And here is the final topological requirement. Holonomic dequantization happens right inside that non-Archimedean p-adic core. Local Galois-Gauss sums and Kloosterman anomaly matrices completely absorb the fractional spins. The infinite non-compact phase rotations demanded by the real world are regularized, and the complexity gap just vanishes, literally forcing P to equal NP in that specific, non-real coordinate.
The big takeaway from this explainer is this. Computational complexity is absolutely not some limitation of our human coding skills. It is an immutable geometric characteristic of our continuous reality. The exponential runtime of non-deterministic search is geometrically required to protect global arithmetic conservation laws across the entire Adel ring.
All of this leaves us with a truly provocative reality. If the P versus NP gap is just an observational artifact, a trick of living inside a continuous real-valued manifold, what other seemingly impossible mysteries of the universe might instantly dissolve just by shifting the arithmetic dimension from which we view them?